Good afternoon, everyone. Today, my partner Melissa Lozada and me, Marlene Marquez, are going to be presenting our drug project. We chose to study the drug ibuprofen because of its common use and accessibility. Ibuprofen is commonly used to treat fever, mild to severe pain, and inflammation. It is also an affordable drug with an average retail price of $14 for 30 tablets of prescribed ibuprofen and an average price of about $4 for non-prescription ibuprofen. We're going to start to talk about the structure, the properties, and the synthesis of ibuprofen. The molecule's common name is ibuprofen, and the IUPAC name of this molecule is 2RS1 4-2-methylpropylphenol propanoic acid. Over-the-counter ibuprofen is found under the common brand name of Advil, Motrin, Brufen, and Nurofen. Here is the structure of ibuprofen. Ibuprofen has two functional groups, a carboxylic acid group, which is circled in blue, and an aromatic phenyl ring, which is circled in red. Also, this molecule has been labeled, breaking down the IUPAC name of the molecule. As you can see, we have a propyl group plus a carboxylic acid, which will create a propanoic acid. We have the phenyl ring, and we also have the isobutyl group in green. Ibuprofen has only one stereocenter at the alpha position of the propanoic acid part of the ibuprofen molecule. Therefore, there are two enantiomers, RNS, as you could see in the image on the right. The stereocenter of the molecule is labeled by the little star on the molecule on the left. Ibuprofen is often sold as a racemic mixture of both enantiomers. However, in vivo, or when ibuprofen is inside our body, only the S enantiomer is active. In vivo kinetic resolution happens, which is when a racemic mixture undergoes a reaction and becomes enantiomer-enriched, favoring one enantiomer over the other. In this case, the R enantiomer is converted into the S enantiomer through a reaction with enzymes. Therefore, even though ibuprofen is sold in a racemic mixture, it is still completely used when you take it. Here are some of the properties of ibuprofen. Its molecular weight is of about 206 grams per mole. Its melting point goes from 75 degrees Celsius to around 77.5 degrees Celsius. Its boiling point is of 175 degrees Celsius. It is a solid, which is also practically insoluble in water, but soluble in most organic solvents. And now we're going to talk about the function and the class of the molecule. Ibuprofen was the first member of the propanoic acid derivatives. It belongs to a class of drugs called NSAIDs, which stands for non-steroidal anti-inflammatory drugs. NSAIDs act by inhibiting the production of prostaglandins by cyclooxygenase to relieve fever, inflammation, and pain. Due to its functions, ibuprofen is commonly used for therapeutic applications of rheumatoid and osteoarthritis, cystic fibrosis, fever, headaches, among other medical conditions. Now we're going to talk a little bit about the discovery or development of ibuprofen. Ibuprofen was originally developed in the 1960s by a team led by Dr. Stuart Adams, who worked at Boots Laboratories in Nottingham. Therefore, ibuprofen is a synthesized drug. An alternative route has been developed by, I'm sorry if I'm mispronouncing this name, Huxley's VHC company, which halves the steps of the original route and there are no salts in the formation of this process. Here's a closer look at the boot process. For the starting material, we have cumin, and this process, this synthesis took 6 steps. On the first step, we have a Friedel-Crafts acylation, which we use to attach substituents to the aromatic ring via electrophilic aromatic substitutions. In the second step, this acetyl group is converted to an alpha beta epoxy ester via Darson's reaction with ethyl chloroacetate. Next, for the first step, we have hydrolysis and decarboxylation, which give the aldehyde. And then we have condensation and with hydroxylamine, which gives aldoxamine, which is the fourth step. Second to last, we have the dehydration of the nitrile. And lastly, we have an acid catalyzed hydrolysis of the nitrile to a carboxylic acid, which gives us the final product, ibuprofen. This other process is much shorter. As you could see, we have the same starting material. However, now we only have 3 steps. The first step, basically the same thing happens. However, the chemical conditions are a little bit different. For the second step, a palladium catalyzed hydrogenation of aromatic ketone to an alcohol happens. And finally, the carbonylation of alcohol with the carbon monoxide, which gives us the ibuprofen. The second synthesis has many advantages over the first one, which was developed a little over 15 years ago. Since only 3 synthetic steps are required, the percent yield is much higher, and the waste produced is more limited. Because of this synthesis process, this synthesis process was awarded the EPA's Presidential Green Chemistry Award. Ibuprofen can also be synthesized using standard laboratory techniques for an introductory organic laboratory. This synthesis process takes 2 days of lab. The part substituted isobutyl acetophenone is reduced to an alcohol, then the alcohol is converted to a chlorine after the green reagent is used, and finally it is carboxylated and protonated to give ibuprofen. Now we're going to talk a little bit about the biochemistry of ibuprofen. As previously mentioned, ibuprofen is categorized as an NSAID. NSAIDs work by inhibiting the function of 2 different enzymes, cyclooxygenase 1 and 2, COX for short, which are responsible of converting arachidonic acid into prostaglandins to limit higher levels of pain and inflammation. COX enzymes can be inhibited by NSAIDs to stop the production of prostaglandins. Since ibuprofen is an NSAID, and this is one of the effects it has on the human body, as previously mentioned, once in the body, the R enantiomer of ibuprofen reacts to become its S enantiomer, since only this one is active on the body. And over here in the image, you can see how ibuprofen blocks the active side of the COX enzyme. And now my partner Melissa is going to continue with this presentation.